Thank you for joining us for our polar session this morning. So my co-chair, Matthew Long, and I kind of struggled a little bit with trying to figure out how to put together a cohesive polar session because these are two very different systems. In the Arctic, the pace of change is so rapid to outstrip our ability to really measure it. Whereas in the Southern Ocean, you know, it's more of a stable system, and we're trying to pick apart the different modes of variability, interannual variability, long-term trends. And so what you're really going to see with these two sessions, the morning and afternoon, are vignettes. We can't possibly tell you the whole story about the important changes in these systems. But we are going to tell you a few things about some notable physical and chemical system changes and how those then impact the ecology. So this morning we'll start with Lauren Kipp, and she'll be talking about some of the physical and biogeochemical system changes in the Arctic.
Hi, thanks for having me. I'm excited to talk to you today about some of my work that was recently published in Science Advances and that I'll be presenting in just 3 weeks as part of my thesis defense in this very room. So if you like what you see, come back on July 20th and I'll tell you more. So rising global temperatures are causing a lot of changes in the Arctic, and many of these changes impact the shelf and the coastal ocean. For example, the Arctic is really influenced by river discharge, and rising global temperatures are shifting the hydrologic cycle and ultimately increasing the amount of discharge coming from both the Eurasian and North American sides of the basin. Rising air and sea temperatures are also thawing permafrost, which is land that has remained frozen for 2 or more years. And because circulating river and groundwaters can't percolate through those frozen sediments, permafrost currently acts as a reservoir of carbon and other organic and inorganic solutes. But if permafrost continues to thaw, that will release solutes and they could ultimately be transported to the coastal ocean. Sea ice is decreasing in both extent and thickness, and that allows for more open water over the shelves so that wind stress can affect the water column and cause increased turbulence and increased mixed layer depths. And because a lot of the Arctic shelves are really shallow, for example, the Laptev shelf is on average 50 meters deep, even a slight increase in mixing or an increase in the mixed layer depth could really increase the communication between shelf sediments and the overlying water column. So together, all of these changes are affecting the coastal ocean, and it's important for us to monitor them and understand how they're changing. Luckily, radium isotopes can help us trace these changes because radium is naturally produced through the decay of thorium in sediments, and it's soluble. So once it's produced in sediments, it will diffuse into overlying shelf waters or be transported to the ocean by river or groundwaters. I'm not showing groundwaters on this figure because in the Arctic, permafrost is thought to prevent much groundwater discharge, but that could certainly become a more important pathway in the future as permafrost continues to thaw. I'm going to be focused today on one isotope of radium, radium-228, which has a 6-year half-life. Because of its coastal source, radium can be used to trace shelf inputs in the open ocean. And so if we see high levels of radium in the open ocean, that indicates that that water was recently in contact with the shelf and the coastlines. And radium itself is not biologically utilized, but other things that come from the shelf are. So radium can be used to trace inputs of things like carbon, nutrients, and trace metals. And so monitoring the changes in radium inputs can help inform us about the changes of these other biologically important species. For those of you who don't think about the Arctic all the time, I wanted to give you a brief introduction to the circulation and point out some main features. So the transpolar drift is this strong surface current that carries water from the Eurasian shelf seas across the central Arctic and then eventually out the Fram Strait near Greenland. And the Beaufort Gyre recirculates water in the western Arctic. I also want to point out on this figure how dominant the shelves are in the Arctic. So over 50% of the area of the Arctic is shelf. And a lot of them are really shallow and wide. So for example, these shelves feeding into the transpolar drift are really wide, and so changes that are happening over these shelves have the potential to impact the open ocean as well because they're carried to the central Arctic and the transpolar drift. So my lab participated in the 2015 US Arctic Geotraces transect, and we went through the Bering Strait up to the North Pole and then back down. So when I show you plots of the water column data, I'm going to separate it into the northbound transect and the southbound transect. We collected both surface and water column samples of all the radium isotopes, but I'm going to be focusing today on the surface samples of radium-228. And I also want to point out that we were not the only geotraces cruise in the Arctic in the summer of 2015. So there was also a German-led expedition and a Canadian-led expedition, and I wanted to give you a rough idea of their cruise tracks because I'm going to show some of their data in a couple slides. And this was a really great opportunity for international collaboration, and it allows us to get a really nice picture of what was going on all across the Arctic in the summer of 2015. So jumping right into the data, I'm showing you the distribution of radium-228 in the northbound transect on the top and the southbound transect on the bottom. And in both cases, the Bering Strait and the Chukchi Shelf is on your left, and then the North Pole is on your right. And so the x-axis is latitude. When I talk about radium, I'm going to talk about it in terms of activities. This is how we describe the levels of radioactive isotopes in the ocean, and it's just in units of decays per time instead of moles or atoms, but you can think of it essentially like concentration. And so the blue colors indicate low activities of radium, and the warm colors indicate high levels. And you can see that most of the Arctic has pretty low levels of radium-228. And that's because it's removed from this shelf and coastal source, and because this isotope has a 6-year half-life, it's had some time to decay. However, in the surface, we do see really strong radium signals. So if we zoom into the top 500 meters, we can see this plume of high radium coming off of the Chukchi Shelf. And then we also see really high levels of radium in waters above 85 north. And this high radium signal correlates with high fractions of meteoric water, which is shown in the black contours. And that's an indicator of river discharge, but it can also be used as a proxy of shelf influence because the rivers are discharging over the shelves and they have to transit the shelves to make it to the open ocean. So if we look at this in a map view, we see this really high radium signal in the central Arctic that I was just saying correlates to the meteoric water fraction. And this was really surprising at first because radium has this coastal shelf source, so we expected the highest concentrations to be over the Chukchi Shelf. And we were really surprised to see such high levels of radium in the middle of the ocean. For comparison, the levels in the central Atlantic Ocean would be about 10 times lower than this. But if you remember back to the circulation schematic I showed a few slides ago, it's actually not that surprising because this is where the transpolar drift is influencing the central Arctic and carrying radium from these Siberian shelf seas across to the central Arctic. So the radium is coming from a shelf, it's just not the one that we crossed on our way into the Arctic. As I mentioned, there was also 2 other geotraces cruises in the Arctic that summer, and the German expedition also crossed the transpolar drift, and so now I'm showing their data here just to show that it does show this same signal with high radium extending back towards these shelves. So once I figured out the levels of radium in 2015, I wanted to see how they compared to historical studies. And so now I'm showing you all of the surface measurements of radium-228 from the Arctic. And you can see that our measurements over the Beaufort and Chukchi shelves are pretty similar to previous measurements, but the high radium that we saw in 2015 near the North Pole is higher than anything that's been observed in the Central Arctic before. And so I wanted to know why this was. And the first things I looked at were whether there was a different water origin between the 2 years, whether it took longer to get there in 1 year versus another, because that could lead to more or less radium decay, and whether this increasing river discharge might contribute. So here I'm comparing our 2015 study on the left to the 2007 study led by Rutgers-Vanderloof on the right, and the black lines show the back trajectories of ice above the locations where we sampled. So I'm using this as a proxy for surface water movement to see if the water came from somewhere different in 2015 versus 2007. But you can see that in both years, it looks like the water originated over the East Siberian and Laptev Shelf seas, so I don't think that different origins can explain the differences that we're seeing. The next thing I wanted to look at was transport time, and ice can help us with that as well. So I've marked the red, green, and magenta X's show the position of the ice 6, 12, and 18 months before we sampled it. So it looks like in both years, the ice, and by extension the water, left the shelf about 12 to 18 months before sampling. But we can also estimate this timescale using radioactive isotopes, in particular the radium-thorium pair. So radium-228 decays to produce thorium-228, and if there was nothing else happening besides decay, these 2 isotopes would reach a state of equilibrium, and they would have the same activities in the water column. But in reality, thorium is particle reactive, so over the shelf, biological productivity removes thorium from the dissolved phase, and we have a deficit of thorium with respect to radium and low thorium to radium ratios on the shelf. Once that water moves off of the shelf, there's less scavenging or no scavenging, and so the thorium will stay in the dissolved phase and will start to approach that equilibrium with radium again, so the ratio of thorium to radium increases. And because we know how fast each of these isotopes decays, we can use that to determine the time scale and see how long it's been since the water left the shelf. So this is how we do that with the activity ratio on the y-axis versus time on the x-axis. If there was no scavenging once the water left the shelf, the progression of the activity ratio would follow this red line. In reality, there might be some scavenging after the water leaves the shelf, so that's what these orange and blue lines are representing. And so we can use the ratio that we measured in the transpolar drift, which is shown in this black line, it's around 0.2, to say that it's been about 6 months to 1 year since the water left the shelf. This approach was also taken in the 2007 study, and they found transport times of about 1 to 3 years. So if we consider both the radium-thorium ages and the ice back trajectory ages, it looks like in both 2015 and 2007, it took about a year to get from the shelf to the central Arctic. And so this is not a big enough difference in transport time to explain the differences that we're seeing in the activities. So it has to be something else. So the next thing I looked at was whether there was more river discharge in 2015. So if there was the same levels of radium in river discharge, but just more river input in 2015, that might cause higher activities in surface waters. But you can see that the levels we measured in 2015 were approximately double those measured in 2007 at the same fraction of meteoric water. So there wasn't more river discharge in 2015, and that can explain the changes. So instead, what I think must be happening is that there's been a change in the relative magnitudes of the sources and sinks of radium to the surface ocean. And so to investigate which sources of radium are most important in the Arctic and which ones are most likely to be driving this change, I constructed a mass balance of radium in the surface ocean. So the inputs of radium to Arctic surface waters include river discharge, shelf inputs, ice-rafted sediment, which can release radium if it's released to surface waters, and advection. And then sinks include outflow and decay. So I can directly estimate most of these sources and sinks using data from the 2015 transect, as well as some other studies we've done, but I can't directly measure the shelf inputs, so I'm going to solve for that source by difference. The river input has two components, so there's a dissolved flux of radium, and then riverborne suspended sediments can also release radium in the estuary. So to investigate both of these sources, we conducted time series measurements of radium in the Mackenzie River and combined that with measurements of radium from some Russian rivers to determine the average freshwater concentrations of radium, and then scaled that up by the amount of river discharge delivered to the Arctic each year. And then to determine the amount of radium that could be released from particles, I conducted a survey across the estuarine mixing zone in the Mackenzie River to see how much radium was increasing in the freshwater-saltwater transition zone, and then scaled that amount of desorption by the amount of particles delivered from rivers each year. The ice-rafted sediment source we investigated using samples of dirty ice, or sediment that had ice that had visible sediment in it that we collected on the geotraces cruise. And so similarly, I determined how much radium was desorbing from that sediment and then scaled it by the average amount of ice melt each year and the amount of sediment that's typically in ice. The advection source is simply the activities of radium in the Atlantic and Pacific end members times the volume fluxes from each of those inputs. To determine the sinks, I needed to know the inventory of radium in the Arctic surface water, so I used our 2015 water column measurements to calculate that. And then the decay sink is just that inventory times the decay constant, or the rate that radium is lost to decay. And then the sink to advection or subduction was determined by dividing that inventory by the residence time of surface waters. So if the inputs and outputs of radium were balanced in 2015, then the sum of my sinks should equal the sum of my sources. And so this is the sum of my sinks in the blue graph, or the blue bar. And the sinks that I'm able, or the sources that I'm able to directly calculate are in green. And you can see that the ones that I can directly calculate only account for about 16% of what's needed to balance these sinks. So solving for the shelf input by difference shows that the shelf is by far the largest source of radium to Arctic surface waters. And this makes sense because the shelves are so dominant in the Arctic and they're such a large reservoir of radium. To put this shelf flux in context, I just wanted to show you how it compares to other ocean basins. So the total flux is similar to the flux from the South Atlantic and South Pacific, But when you normalize the flux to the basin area, it becomes apparent that the shelf flux is really important in the Arctic because it's a small ocean basin. And so this bottom plot is showing the flux normalized to the basin area. So if the shelf is the most important source of radium to Arctic surface waters, and the amount of radium in surface waters has changed over the last decade, then this increase is likely being driven by an increase in the shelf flux of radium to surface waters. And there are a couple of things that I think could be driving this change, and I touched on some of them in the beginning of the talk. Increased coastal erosion might be causing more sediment delivery to the coastal ocean, which can release radium. Permafrost thaw could be allowing for more submarine groundwater discharge transporting radium. And increased wind-driven mixing could be stirring up radium from sediments. I've done a back-of-the-envelope calculation to determine the magnitude of the coastal erosion source, and it's only about 2% of the total shelf inputs, so I don't think that the magnitude of that input is large enough to be driving these changes. Similarly, permafrost is still really widespread in the Arctic, and it's thawing at really slow rates, so I think that it's unlikely that an increase in submarine groundwater discharge as a result of permafrost thaw is large enough to be driving the changes we're seeing. I think the most likely mechanism is an increase in wind-driven mixing as a result of the loss of ice cover over Arctic shelves. So this figure on the bottom is showing the possible scenarios in 2007 and 2015, where in 2007, if there was more ice coverage, that prevents wind stress from affecting the water column, so there's less mixing and turbulence. Whereas in 2015, if the ice has receded off the shelf, then you can have more wind and wave action, increasing the turbulence and essentially stirring up the radium from shelf sediments into the overlying waters that can then be transported to the central Arctic in the transpolar drift. So to see if this was a viable explanation, we determined the average number of open water days in the Arctic in the 5-year periods preceding sampling in 2007 and 2015. And so the 2007 period is shown in A, 2015 is in B, and then this last panel showing the difference between the two time periods. And so indeed there were more open water days before we sampled in 2015 over the Laptev Shelf and a little bit over the East Siberian Shelf. So I do think it's possible that this mechanism is driving the increased mixing. If you take nothing else away from this talk, I want you to know that radium is a good tracer of shelf inputs to the ocean. And so if this increased flux of radium is occurring, then that implies that there's also been an increased flux of carbon, nutrients, and trace metals coming from the shelf. And that is really important, especially in combination with the loss of sea ice, because the loss of sea ice is changing light limitations, and this study is showing that nutrient limitations are also likely to be changing. So overall, this increased flux of shelf-derived materials is important for both the chemistry and biology of Arctic surface waters. And we should consider it as we think about how climate change is affecting this region. So with that, I will put up my acknowledgments. I'd like to thank the captain and crew of the Healy and all the scientists on the Arctic Geotraces Transect, Peter Slosher's and Bob Newton's group at Lamont to determine the water mass fractions, and then WHOI Graphics made the great shelf figures, and Grayman and Hall took all of those. And thank you to my funding sources. So I'll be happy to take questions. Rachel.
Hey, thank you for the great talk. So you were showing what was happening over the Laptev Shelf and in the transpolar drift. I was just wondering in other areas, say the Beaufort Gyre, which you sampled, do you see, it looked from the figure you might not be seeing changes, so do you think shelf input isn't changing there?
Yeah, so based on these plots, I think the reason we might not be seeing changes is because it doesn't look like there's been a big difference in the number of open water days. In both of these, it looks like there just was a lot of open water in both cases, so I don't think that it's changing as much there as it is in the Eastern Arctic. So the Eastern Arctic is experiencing some of the most severe warming trends, and so the changes in the ice coverage are affecting that region a lot. And so I think that might be driving changes. There are also really shallow shelves in the Eastern Arctic, so even a small change could increase the communication between the shelves and the overlying water.
Do you think as warming continues, that actually the western shelves might be?
Yeah, it's a good question. It's a good question. I think If there's already not a lot of ice cover, I don't know how much it will change, but certainly if there are more storms happening, then that could drive increased mixing in all regions. So I do think it will change, and we need to keep studying it, keep getting measurements from different shelves. I think in the Beaufort Gyre, there's still a lot of ice coverage, so I don't think that is being affected as much. Yeah.
Is there a chance that there's a lot of inter-annual variability that just one time happened another year without radium and the other time here because there are so few measurements?
Yeah, exactly. That's a great point. Again, a plug for doing more studies. So there is Rutgers van der Loof recently published a study that also has a 2011 transect in it, and he saw a pattern of radium versus meteoric water that agrees well with these two studies. So that gives us one more time point that shows it's not just a fluke that we saw it this one year. But certainly we need to keep studying to determine whether it's a continuous change and what the rate of change is, whether it's just a one-time thing or if it's a slow increase.
Hi, this is a wonderful talk. I didn't quite understand your rationale that the shelves being the normalized greatest contributor leads you to suspect them as being the cause of the change. Why is being the normalized largest contributor more important than being the largest contributor itself?
It's not. I was just making a separate point that shelves are super important in the Arctic. So just the shelf being the largest source in itself is the reason why I think that's the change. But then just to give you some context for the amount of radium coming off the shelf in comparison to these other ocean basins is why I was showing this figure. Okay. Sorry, that was confusing. Okay.
Thanks, I thought that was a really great talk. I had a question about the river input, and you might have covered this and I just missed it. But you had looked at one river and had suggested that rivers weren't a source or weren't the cause. But I'm wondering if you had a shift in hydrology, you had the same amount of fresh water coming in, but from a different location with a different particle load, that could also explain larger radium input.
Yeah, so I think changes in the river input of radium will certainly impact the radium in surface waters. I just think that because rivers are only like 3% of the source, even if that source tripled, it's not going to be the main driver. But I do think that we will see changes, especially as permafrost starts to thaw and the solute loads might vary.
Do you have an idea of the residence time of the water in the basin Arctic and how that would influence your results, given the half time life of radium?
Yes, sure. So I used an estimate from Peter Slosher. I can't think of the year, but he estimated the residence time of surface water using tritium-helium ages and estimated about 3 to 10 years. And that range is the error bar on this sink, because that is a really big difference. But even the lower limit of that is like right there. So even if we assume the most conservative estimate, it still won't change the result that much. But that's what this huge error bar is the difference in the surface water residence time. Thanks.